Consider a sample with n equals to 10 scores and a sum of squares of 90. If you were informed that these scores make up a population instead of a sample, the sum of squared deviations would be equal to which of the following values? 90, greater than 90, less than 90, or not enough information. Okay, so what do we know here? We know that n equals to 10 and that the sum of squares equals to 90. And so that's when it's a sample. Now they're suggesting, what if we found out that it's a population? If it's a population where big N equals to 10, they want to know what would the sum of squares be equals to. Well, it's not going to change because the formula for sum of squares, if I'm dealing with a sample, so let's put sample stuff on this side, my sum of squares has one of two different formulas. It's either going to be that the sum of my individual scores minus my sample mean squared. So the sum of my squared deviations from the sample mean, that's going to give me my sum of squares, or it's going to be the sum of x squared minus the sum of x in brackets squared over little n. Compare this with the formulas for population. I still, if I'm doing the definitional formula, am going to have the exact same layout of formula, just that I put in a population mean instead of a sample mean. So if I find out that this was a population instead of a sample, I would use this formula instead of this formula. But I've got the exact same layout of a formula here, so it's not going to change the math at all. Same thing if I was dealing with a computational formula. I would still be using the sum of x squared minus the sum of x in brackets squared over, in this case, large N. Large N instead of small n, it doesn't make any difference. I'm going to get the same result. So if it was 90, it's going to stay 90.